Hello, everyone. Welcome again to ACE. Today, we are going to have an interesting paper, but to start with, my name is Omar Nada. I am a senior data scientist at RBC, and I am the Commander Systems Team Owner and Research Head at Aggregate Intellect in ACE. So, to give a quick introduction about ACE, ACE is a community of machine learning practitioners and researchers where we get gathered, we invite authors to speak about their papers and their work, engineering, and different products. We host live sessions like these 3 to 5 times a week. And we also produce a premium content in different topics and areas that you can get involved in. Please visit the AI.science website and you can find all the videos that we have. You can also subscribe to our channel, ML Paper Explained, to get notified about all the papers we have there. I also have Susan, who is the reinforcement learning reinforcement learning stream owner. She's featuring in this video. And finally, not like at last but not least, Olivier, who is the main author of Joint Policy Value Learning for Recommendation. And we are going to talk about how to basically use reinforcement learning with its different techniques in refining recommendations. It's all yours, Olivier.
Okay, thanks, Omar. As mentioned, this paper is titled Joint Policy Value Learning for Recommendation. It's joint work with David, Flavian, and Martin from Criteo, and it's going to appear at the KDD conference in a little under 2 weeks. So let me first very, very briefly talk about why we do what we do. So it's only a super short primer to Rexis. So many web services need to match users with certain items. This can be like a song or a movie or a news article, for example. And these systems then, they basically try to figure out which are the relevant items for a certain user. And why do we do this? Well, this is to combat the user suffering from a certain overload of information when you have a very large sort of item catalog. And of course, these systems can also generate value for the sort of business. So how do the sort of existing approaches do this? Well, they sort of look at users browsing certain items on a website. So for example, if you think of a retail website, we can see a user that is looking at music-related things. And then the main question that these systems actually try to answer is, which are the sort of other items that the user saw in that session? And this works pretty often, but there are some things wrong with this view. So the main thing is that we're actually, when you are doing it this way, you're trying to frame the problem of recommendation as trying to have some sort of autocomplete of the user behavior. So you try to figure out what the user actually already did without the system being there, which is of course going to be very different from having a system that is going to try to have some sort of optimal policy that is going to do a certain intervention, as in show a certain recommendation, and then you would have some system that you want to maximize like the sale uplift or something like that. And of course, when you're going to have an online evaluation with those sort of super fancy KPIs, but your system is evaluated completely offline as basically trying to predict the next item that the user already found themselves, these things are not going to match. And this is really something that you see really often in the research these days. So for the purpose of this talk, we're going to talk about CTR as the main metric that we want to look at. So that's the number of recommendations that actually get clicked on over the number of recommendations that you show. And when you're focusing on something like CTR, it makes much more sense to frame the entire thing as some sort of off-policy reinforcement learning problem. So here you have a certain agent, which is going to be us. We're going to show recommendations to a user, and then we're going to observe whether the user clicks or doesn't click on these recommendations. So the main question that you ask here is, which are the actions that I should take to obtain as much clicks as possible? Now, this is all very fancy and fun, but it's not super straightforward to evaluate these systems now. Suppose you have a system like this, and you are logging the things that are happening. So you know the recommendations that were shown to a user and the reward that you observed. So the user clicked or didn't click on these recommendations. And now you have to figure out for two different systems, which system is actually going to perform better in a live setup. Now, this is not super straightforward because some recommendations weren't shown to the user in your training sample, but you still need to figure out which one is more likely to actually lead to a click. So how do you actually do this? Well, there are three main options to do evaluation. The first one is when you have an explicitly randomized data set with very carefully logged propensities, then you can adopt some things from the sort of off-policy RL world, but these are not super straightforward to actually use. And the main problem is that most, there are a few of these data sets available, but really not a lot. A second option is to do something like an A/B test. Of course, this would be great, but it's super expensive, and it's not super easy for most of academia to actually do something like that. So if you don't have any data sets, and you don't have any experience online either, then there is one third final option, and that is to use a simulation framework. And while these can actually be very nice to work with, you need to make sure that these actually reflect the real world environments as well. And we're lucky because a few years ago, there was such a reinforcement learning simulator for the problem of product, a reinforcement learning environment for the problem of product recommendation in online advertising was proposed at the Reveal workshop at Rexis 2018. And it's called RecoGym. And what does RecoGym do? Well, on one hand, it simulates the organic interactions, which is what most people used in like the first sort of days of recommendation, where you just observe what the user does with the sort of different items in the item catalog. And then they also have the bandit interactions that they simulate, which is a certain agent is going to show recommendations to a user, and you will observe whether or not the user actually clicks on it. And what's great about this is that now you can use the bandit parts to actually simulate A/B tests as an evaluation tool without actually needing a live deployed system. So you can simulate different cohorts of users. You can let them sort of interact with different sort of agents that you have. You can measure the simulated CTR that you then observe, and then you can see which sort of agent was actually able to learn the most effectively of your sort of training sample. And we are going to focus on the setting where we actually use this as an evaluation tool throughout the rest of this work. So that's all very nice, but how do these agents actually work? Like, how do you actually learn from bandit feedback? Well, this is not super straightforward because you will never observe the reward for an action you did not take, and you cannot show the entire item catalog to a user as a recommendation. So you need to have some smart tricks. First, let's start with a little bit of notation. So we're going to assume that we have a stochastic logging policy by 0 that is going to describe a probability distribution over actions conditioned on a context. So what does this mean? This basically means that when a user comes to your system, you're going to sample from a certain probability. You're going to sample from a certain probability distribution the action that you are going to take, which is the item that you're going to show as a recommendation. This is going to be stochastic because if you will always do the exact same thing, it's going to be much harder to learn, of course. So assume we have a data set of logged feedback coming from such a system working live. So we're going to have a certain context vector, which is going to be the user state, the user that is coming to our system. We have a certain action identifier, which is the recommendation that we showed to that user. We have a logging propensity, which is the probability with which that action was actually sampled to be shown to that user. And we're going to observe a reward. For this work, it's going to be a binary reward that we will sort of get when we show recommendations. So no long-term stuff, no fancy stuff like that, just a binary simple reward that is already hard enough. So assume you have a data set like this, you want to learn a recommender. The most straightforward way is to start off with a value-based method. So what you're going to do there is you want to model the probability of a click conditioned on an action in a context. So given a certain context action pair, you want to know which action is actually the most likely to lead to a click. When you have a binary reward variable in a linear model, this is actually logistic regression. You can basically try to optimize these parameters through maximum likelihood estimation. This is all very, very standard stuff. But the main problem here is that your context action pairs are not going to be sampled uniformly at random. Your logging policy is probably going to do some actions more likely because it hopes that they will lead to a click, and some actions that it might think are very poor might not happen very often. So the quality of the estimate is going to be very, very sort of unevenly distributed. For the context action regions that are not well explored, you will have very, very poor estimates, and this might be a big problem. So if you don't want to stay with these value-based methods, you can also look at a second family, which are the sort of policy-based methods. They don't directly basically try to model the probability of getting a click, but they directly map a context to an action. So they basically try to answer the question, how many clicks would this new policy by theta would have gotten if this policy was deployed instead of by 0? So how do you actually try to optimize something like that? Well, the sort of most straightforward approach here is to look at something called an off-policy contextual bandit. So what we're going to do is we're going to have a linear model with a softmax at the end. This softmax is going to ensure that we have a probability distribution over actions in the end. And once you have that, you can actually try to optimize the sort of parameters theta that you have here to optimize some notion of the counterfactual reward. What that means is we are going to go over the training sample, which is this sum here. We're going to look at the items that actually got clicked, which is why we multiply with the C here. It's going to be 0 for non-clicks. It's going to be 1 for the clicks. And then we are going to basically try to maximize this ratio, because that is the only thing that we actually sort of can do, because these are all just the variables that we have in our data. What you have here is the probability of the action that led to the click actually being taken by your new policy divided by the probability of that action being taken by the old policy. So you are trying to maximize that ratio. So although this looks like a very fancy formula, what it does is the stuff that worked in the training sample, do that more often. That is basically the main sort of idea behind this. Now, this works rather well, but of course there are some problems here too. The main problem is that this ratio of probabilities is essentially sort of unbounded, which means that you can get very, very high variance on this estimate, and then it won't work well. The main problem, the second main problem, is that 0 reward samples are ignored. As you can see here, when the reward is 0, this is not going to affect the probability of the action that leads to a 0 reward is not going to affect your final estimate. And this is also very likely to lead to problems like propensity overfitting, which I will not be dealing with in this talk. Right. So these are methods that already exist for learning from bandit feedback, but we are looking at the problem of recommendation, which is not entirely the same. What we are actually dealing with is a situation where you have stochastic rewards. So sometimes you might get a click for a certain action, sometimes you might not get a click for a certain action, and you might not know why. So your model is basically is always going to be misspecified. So if you think about a setting like this, and you think about that same formula, which is basically called the standard, which is the standard IPS estimator. What this is going to do is when multiple actions are going to actually work for a certain context, this is going to put all the probability mass on the single action that worked best. Now, doing this makes sense if you trust your training sample, going purely for the empirically best action. But if you have a stochastic setting and you have a finite training sample and you have high variance, this might actually not be something that you want to do. So how are we going to solve this? Well, we're going to look at a lower bound of this estimator. And this lower bound is going to not deal with the direct sort of probability here, but the logarithm of the probability. And this is a lower bound of the original objective. And this has recently been proposed to actually reduce the variance of the estimator and promote a learned policy that's going to explore more in recent work. But we are actually focused on looking at how this is going to transform the objective when rewards are stochastic. So to look at that, we're going to deal with a small sort of toy example. First, I'm going to drink a little bit. Right, so looking at a sort of toy example. Suppose you have a multi-class sort of classification setting you have a certain class A, a certain class B. You have a banded feedback setting, so you can guess either A or you can guess either B. And then you will observe a 0 or a 1 for that action that you took, but you don't know anything about basically the sort of different actions. So you want to learn a policy that is going to pick the action A or the action B in this setting. When we have a multi-class reward, this means that one of the two is going to be the right class or will lead to a click, and one will not lead to a click. So for this very simple setting, assume you have that, and assume that the action A is actually the one that is the true class, the one that will lead to a click. Then, of course, the normal IPS estimator, which you can see on the left y-axis on the blue line, that one is going to be maximized by putting all of your probability mass on the action A. Of course, it's worst if you put no mass on action A, because then you will never get a click. If you look at the lower bound, which is the red line or the rightmost y-axis, you can see that this will largely agree. Like, it's going to be maximized by putting your mass entirely on action A, but it's going to be a little bit different on the other end, because here it's much more smoothly sort of going down, and it's going to minus infinity for 0 here instead of just going to 0. So that is the multi-class setting, which is somewhat interesting, and it's been used a lot for the evaluation of these methods in sort of previous work, but it's not really very close to what we want to achieve in a recommendation framework, right? This would mean that there is one single item that will lead to a click, and much more likely that multiple items are actually likely to lead to a click. So then you can look at a multi-label setting. So suppose that for this same sort of toy example, both the action A and the action B lead to a click. If you have that, the normal IPS estimator no longer cares, actually. Like, it really doesn't matter if you put mass on A or mass on B. They're both going to lead to clicks the entire time, so it's all the same. Whereas when you now look at the lower bound, it's a little bit different. They're still going to agree on the optimum, which is going to be at 0.5 here. But when you have a policy that is more sort of to the extremes, this is going to be bad, because the probability of 0, the log of 0 is going to be minus infinity. And that is now going to be the case when you put 0 mass on A or 0 mass on B. Now, where things really get interesting is when you no longer assume a deterministic reward. So assume you can get some clicks on A and some clicks on B, but you're not guaranteed to get clicks on A, you're not guaranteed to get clicks on B. If this happens, you basically see that the lower bound is actually really going to help you here. So when you look at the normal IPS estimator, it is still going to be the exact same, right? So in this setup, we have 2 clicks on A and 1 click on B. What this estimator says is, okay, we can basically forget about B. We need to put our entire mass on action A. That is here. And then we're basically doing our best. But the lower bound can no longer do that, because when you're doing that, you're putting 0 probability mass on action B, you're taking the logarithm of that, and you're going to minus infinity. So the lower bound here is going to promote a linear allocation of mass that is proportional to the rewards that this action actually sort of got in the training sample. So that is here going to be 2/3 for action A and 1/3 for action B. Okay, so for this very, very simple example, we can really see that the lower bounds might actually really make sense to use in settings where you have stochastic multi-label rewards, which is exactly what we have in the recommendation set. So it's a more strict version of the normal inverse propensity scoring estimator. If you miss a single sample completely, so you have a 0 probability, you will get an infinite loss. It's going to take into account basically all of the positive samples instead of just the empirical best arm because of this, and this will lead to less overfitting. What's also nice is that it's going to make the objective more convex, which is going to be much, much easier to actually optimize it. And it's very easy to sort of plug this into many, it's also very easy to plug this into many previously existing policy learning methods. Okay, so that's the first part. But why is this paper actually titled Joint Policy Value Learning? Well, that's the second part. So we have shown the family of sort of value-based methods and the family of the policy-based methods. And we have highlighted what's wrong with them. So the main problems with these sort of policy-based methods is that they don't look at 0 reward samples. So if I show a certain recommendation 1,000,000 times and I never get a click, this is not going to impact my reward estimates. It doesn't matter how much mass I put on that action. Now, this is not something you want, right? If you know it doesn't lead to a click, you don't want to do it. There's also going to be very high variance on your estimate, which can be a problem. And you have this sort of spurious issue of propensity overfitting as well. Now, what's wrong with value-based methods, on the other hand, is they don't have a way to really use the propensity score in a smart way. And this means that the sort of context action regions that are not explored well, they will have very bad estimates. And this is really going to screw up your method, basically. So how do we get the best of both worlds? Well, it turns out that you can write them to actually have a shared shared parameterization, which I will not go into detail here, but you can find more stuff in the paper about that. And because of that, it sort of becomes really easy to basically try to optimize the methods for a weighted average of the two loss functions. And that is what you see here. So now for the dual bandit, we are actually going to look at the parameters that are going to maximize the CRM approach and the negative log likelihood as well. And that is actually going to be much, much better. Because here, now we are using the negative reward, the zero reward samples in this part, in the likelihood part. And we're also going to be actually able to use the inverse propensity score from the CRM part as well. Okay, so does this actually really work well? So we're going to go over some experimental results. So what are the research questions that we want to answer? Well, this logarithmic lower bound, does that actually work? And if so, how and when? These various methods that I've been talking about, the value-based ones and the policy-based ones and the joint policy value-based ones, how do they actually compare in terms of performance? So the policy and the value-based methods, they were all proposed for a simulated bandit feedback setting, but they haven't been evaluated in a recommender setting yet. And if so, like, do some methods work better with a very good logging policy? Do some methods are some methods more sensitive to a bad logging policy? Are some better with small action spaces, or do some methods work well when you have a large training sample? These are basically like the main method, the main questions that we wish to answer. So for this, we're going to look at 3 different logging policies. The first one is going to be realistic but hard to learn from. So here we are going to look at, we're going to sample the actions that we're going to show to the user based on the organic interactions this user already had with certain items. So this means that we're going to sample from a very small set of the entire action space, which is going to be very realistic, but it's going to be super hard to learn from, because if you put, if your logging policy has 0 probability mass on certain actions, this means that it doesn't have support over the entire action space. And this means that the assumptions that you're making to basically do this math, they no longer hold. You are not supposed to use inverse propensity scoring in this setting. And although that's true, this is all, this is much more sort of a realistic case, because you will very seldomly have a live system that is going to be able to randomize over the entire action space. But okay, if we want to look at something that doesn't violate our assumptions, we can also work with this logging policy in combination with a sort of epsilon greedy approach. So for a very small probability, we're going to take an action uniformly at random, and for 1 minus this sort of epsilon, we're going to go with the previous logging policy. This is already a little bit sort of idealized, because many systems will not like to actually show completely uniformly random stuff to their users for a very small portion of traffic even. And it's also still going to be very challenging to learn from, because for very small values of epsilon, it might still be that certain context action regions are not well explored, and this is going to be a problem. And for a sort of for very large values of epsilon, you are going to get a uniform logging policy. So this means that you're just going to show your actions uniformly at random, which is completely not realistic and much simpler to learn from. But still, it's a nice thing to simulate with RecoGym to sort of check that we're actually doing something that makes sense. Okay, so what we have here are results from a simulated A/B test. So the 3 different plots are actually the 3 different logging policies that we consider. the lines in the lines in the different colors are going to be the different methods that we proposed. And you're going to see more training data being fed to the algorithm over the x-axis, and the y-axis is showing the CTR that these methods then actually get in a simulated A/B test. And here we have an action space of size 10, which is rather small, but still. The main thing you see here is that for uniform logging policies, it doesn't really matter what you do. Like, many methods get very close to the sort of skyline, which we're not able to attain, but this is like the maximum that you can get. So like, this is like the very simple case. It becomes more interesting when you move to a setting where you have much smaller epsilons or no epsilon at all, and you will not be exploring the full action space. The main thing we see here is that the value-based methods is really going to decline. So that is the sort of orange line. It's really going down here. So here you see that it starts off being much worse than the contextual bandit, and then for a certain amount of training data, it's going to become a little bit better. But the dual bandit is actually able to use both the information. So the line you see here is actually going to use information from the contextual bandit as well as the value estimation. And the logarithmic lower bound, you can see that one as the light green line compared to the dark green line. You can see that here as well, for the harder cases, it actually works really well. So you can see that there is a significant improvement from using the logarithmic lower bound over the normal sort of IPS estimator. But you can see that that is not true for all settings. So in this setting, where you have an action space of size 10 and an epsilon of 1%, so 1% of your actions are going to be uniformly at random, you can see that this actually hurts performance. And we're going to sort of come back to why that is. And if you want to look at larger action spaces, we will see that we see largely the same trends, but the results become a little bit more pronounced. So we can still here see that the dual bandit is performing better, but in the uniform case, it doesn't really matter what you're doing because it's an easy case. When you are getting much less randomization, you can see that the value-based method is doing decently, but it's already doing less good as with the smaller action spaces. And you can see that the off-policy contextual bandit is also doing great, but the dual bandit is still able to improve upon both those methods. And then for the logging policy that doesn't have support, we can also see again that the dual bandit is doing great, but here the value-based method is really doing very, very poorly. And the reason here is that most of the actions were never sort of taken for a certain context in the sort of training sample, and that is why you get very, very bad estimates, and that is why your system doesn't know what to do, basically. And then finally, we also have an action space of size 100, and here you basically see the same trends. So where for very small action spaces, the value-based methods were actually doing really well, here they are really, really not the best in class. And here you can see that it's much better to use a sort of policy learning method, which is the green line here, which is a little bit higher is the sort of purple line, which is the dual bandit. And then you can also see that something called POEM, which I haven't really talked about, is also a really good method in these cases. But in the hardest case, where you don't have support over the entire action space, you can really see that the dual bandit here is significantly better than the other ones. Okay, so the key observations: logarithmic IPS, it can help when the logging policy doesn't have full support, but it can also hurt performance actually in some other cases. And the main reason that we think this is happening is because you are being very conservative. Like the lower bound helps when you don't fully trust your training sample, but the settings we actually simulated, you know the logging propensities, so you can actually trust your sample. But when you don't know these logging propensities and you would have some sort of estimate of them, a very small error can mean the world. And then this lower bound is going to be much safer to use than the normal sort of estimator. We can see that whereas it doesn't really matter which method you use when you have a small action space in a uniform logging policy, when you have more deterministic logging policies and larger action spaces, the value-based methods are the ones that are most impacted, but the dual bandit is actually sort of good at being the best, basically, in most of the experiments. So to conclude, we have advocated for Recogen to enable research in counterfactual learning for recommendation. And the main reason for this was that we don't have any data sets, basically, and we don't have access to live experiments. So this is the best we can do. We sort of went over a few existing methods. So we showed where they tend to fail. And then we proposed two solutions, which is a lower bound for the normal inverse propensity scoring estimator and the joint policy value learning approach, which is the dual bandit. As future work, we wish to study the relation between the dual bandit and doubly robust approaches, which also have an explicit reward estimator. We want to look at larger action spaces because 10, 25, and 100 is still very, very small for the real sort of Rex's world. And we also want to look at multiple iterations of logging and learning, where you really have a learned policy as a logging policy and not just one of the three simpler ones that we sort of talked about. Okay, this is the end. I would like to thank you all for your attention. The source code is online, and I'd be very happy to take some questions.
Awesome. Thanks a lot, Olivier. So for all of our audience, please ask any of the questions you have on the YouTube channel, and I'll take them to Olivier. Till that happens, I have a couple of questions, if you don't mind. Okay. So for just to be clear, the concept is you are using a logged policy, which is from whatever model, recommended model that already generated some recommendation for a given user. And then you're taking that log data. So if that recommendation has been interesting to a user that they clicked on it or not, you're taking that data and then you're building the dual bandit on that specific data, right?
Yes.
Okay. So is it safe to say that as long as I have that data, it doesn't matter what model generated that data, so it's technically model independent, so you can just build this on top of any model?
Right. So the main thing is that you need a stochastic logging policy. So you need a system that is going to randomize when it's actually showing stuff, and that might be a problem. Also, we assumed to have the logging, we assume that we know the logging propensities beforehand, which is also something that is not super simple. So when you have a system that is really sampling in production and is saving these weights somewhere, then yes, it doesn't matter what that model is, but you need to know like the source of randomization to make use of important sampling.
Okay, that kind of makes sense. And so my understanding is the awards is either good or bad, so 0 or 1. It's a binary awarding system. But in recommendations, it's really not that extreme, right? It's not either 0 or 1. It could be, it's a good option. It's not the perfect. So how do you see it working with a continuous rewarding system?
Right. So I don't think that would be a big problem, actually. So like we mainly assumed a binary reward, and then we went with a logistic regression model for the value-based methods. I assume you could just use something like a ridge regression model there for a sort of a normal rewards. And for the contextual bandit, it actually doesn't really matter. Like there, the scaling of the reward is important. But it can be something continuous instead of just something sort of.
Okay. But then
I mean, sorry, and then I'm assuming like then you have those two things, and then you can just use the sort of dual bandit with a sort of combination of the CRM approach and something like a ridge regressor instead of the value-based method that we looked at in this work.
But the only thing I see about a continuous rewarding system is it's going to be very biased towards specific actions. Because when you're doing a binary, 0.8 and 0.9 and 0.6, they're all considered 1. Right? So you have a lot of more pull in what to be recommended next or what is considered a good action. But if you have a continuous rewarding system, it might be the fact that there are very few items that have high probability, therefore it will be taken most of the times. Do you see this a problem?
Right. So then I think it would depend on how you scale the rewards, basically. So if I think of something like a sort of continuous reward, it can be something like on a news article website, you have like the time that the user actually spends reading the article. Then I assume it's probably bad to just scale it like that, because then you might have like a 0 if you don't read the article, a 1 if you read it for 1 minute, and it's sort of, there's no bound. If you sort of click on the page and it's open for a few hours, it'll be way too much. But so I mean, I don't think this is a problem if you scale the rewards sort of well, but it might be a problem if you don't do that. But I would say that that's true for most methods that actually deal with those rewards.
Yeah, you're right. It's
actually, to add to that, like, I'm wondering, do you think that if there's a continuous reward, like, would it be able to capture a bit more information as opposed to like binary, like in terms of like relative like goodness or
right? Yeah, I mean, certainly, I do agree, but then of course, first of all, that would have to be simulated by Recogym, which it doesn't support right now. And also, I mean, it's becomes harder to think about, right? Like I sort of don't really know of a lot of work that uses rewards like that. It's much harder to stay, like, it's not super general, I would say, most of the time. When you think about stuff like dwell time, that might be important for a news article, that might not be very important on something like a retail website. So I'm not sure. Like, I mean, I do also agree that CTR is not the best metric to look at, but it is sort of like the most universal one we have right now, I would say.
Yeah, I guess, okay, I think I see the way that, let's say it's continuous, but making it so it works is like you transform the continuous rewards into like a rank as opposed to like an absolute value. I guess that might be a feasible way of capturing
right.
the ranking value. I guess this is pretty common in Rexis as well to do that.
Right, but yeah. Wait, let me think, because I would say, like, if a user clicks on 2 recommendations on your website, you don't really know which one is better, right? You just know that you got 2 clicks, so you basically get 2 binary reward signals. But you don't know that one was actually better than the other one. So although it's really interesting, I'm not sure if you can actually extract something like that.
But then, as you mentioned, if you're using the implicit information, which is basically how long did they click for, if they clicked on that specific item more than once, these are all will make it
right.
more granular. Yeah.
Right. Okay. So I mean, it certainly is an option to use that signal when you have it, but I don't think it's super straightforward to have it. But when it's there, you can certainly exploit it with a method like this as well.
Actually, so talking about this, right? So you're saying if a user click on an item, 2 different items, right? Do you think the sequence matter in this case? So the first item has more weight than the second item, or the second item has more weight than the first item? Do you think that will matter?
In real world systems, certainly. So I certainly think that works on recommendations that they're actually based on the sequence of items in a session. I think that is very, very important. Again, that is also not something that we actually looked at here, because it's also not being simulated by Recogym right now. But that certainly would be something interesting. And then you would maybe not have like a very simple model like we had for the value-based parts, but you can have something like a sort of RNN or something like that to really try to learn that sequential nature. But that certainly would be feasible to do that in this sort of framework too.
Yeah, like we definitely, like, personally, we tried different RNN models to, or attention specifically for that aspect. But then I was thinking, if we decide to use reinforcement learning for a session-based setup, right? I still feel it will be a good fit, because you are learning, you have a sequence of items. Yes, the sequence is more fitted towards RNN, but at the same time, I see it as, okay, so I'm in action X -1, then I'm going through my action spaces to see what is the next best action, and I'm learning from it. So don't you think still it will be actually a good fit for reinforcement learning? Maybe not the specific model, but generally.
Certainly, yeah. There is a paper at SIGIR 2020, which was just last week. It's called Self-Supervised Reinforcement Learning for Recommender Systems. I think I said that right. And this one actually deals with sort of this setting. So it's basically trying to combine session-based recommendations with the sort of reinforcement learning paradigm. And it's also a really nice paper, so I would certainly invite you to sort of read it if you want.
Well,
Nice. Actually, I have a question that's kind of, it could be more of a future research type of thing, because I'm wondering, first of all, for the logging policy, do you, for each kind of experiment, do you keep the logging policy, I guess, the same throughout? Like, do you ever have, let's say, one logging policy and then in the same, let's say, iteration, and then you swap for another more complex logging policy, let's say, and then in the same experiment?
We don't have that right now, but that is also super interesting. So there is a paper by the group of Torsten Joachims, I think KDD 2017, if I'm not mistaken, where they look at this for, I think they started out focusing on the sort of counterfactual evaluation. So how do you basically evaluate a method when you have a data set that comes from a few different logging policies? And they have some super nice work on that. So that's, I think it's sort of KDD 2017. And then they also have a sort of follow-up paper that then is more about learning in these settings instead of the first one. And that is also like super interesting stuff. We haven't looked at it yet, but it's certainly on the list as well for me. Because I mean, that is something that you might have pretty often, right? Like you don't just have data from a certain logging policy. Your system actually ran some sort of A/B test or a few A/B tests. So you have different logging policies running at the same time, and you want to use the entire data set as fluently as possible. And then you need to think about some sort of special tricks then as well.
Yeah, definitely. And I think just to quickly explain my question to the audience as well is, let's say you're on some sort of website and they were running, like Olivier was saying, like different tests. Like maybe today I was subject to test A, and then I clicked on certain things. But basically the stuff that I clicked on was impacted by actually policy A, but then tomorrow I get policy B. And then some of my actions are impacted by policy A, and then the next day my actions are impacted by policy B. So it becomes important, I guess, in production, and to think about it if it's very detailed, to think about that. But of course, in like a more simplistic environment, then that is more of a just extra thing to do.
Yeah, of course. I would say it's always best to really start with the basics. But if you would want to use something like this in your real world system, that is certainly a very good thing to sort of basically try to think about. Because when these logging policies are very, very different, what they show in the original paper is that then you can really get high variance. And it might actually be better to just use data from a single policy than to learn from data using both policies, because it might actually be that you get worse estimates because the data is so different. So when you would do something like that, you really have to think about what you're doing and really make the fact that you have different logging policies very explicit as well.
I actually have a question from Serena. So Serena is another stream owner with us at AISC. So she's in equation number 6 on the paper, right? She's saying, so can you please clarify how the decision rule A star incorporates the logging policy pi 0, because it is not in the equation. Yeah.
Okay, so I don't have the sort of paper right here in front of me, but the right. So I think I know what she means. So the thing is, your decision doesn't include the logging policy because your decision is based on your model parameters, and your model parameters are based on the logging policy, right? So your model parameters are going to try to optimize some notion of certain counterfactual rewards, right? And then once you have these model parameters, you're going to use these to figure out what to do when you have a new context. So that is why you don't see the logging policy in that sort of equation.
Okay, that kind of makes sense. So can you actually, so in the like, I think slide 24, 25, you had logging policies explained.
Here.
Yeah. So basically, like, can you quickly go over those again? Because I think the logging policies is the critical part in this paper.
Right.
So yeah, can you go over that quickly?
Right. Okay. So the first logging policy that we have is it's called organic popularity. But what it basically does is you're going to sample according to how often the user has basically seen this item in the past, in a completely sort of organic way. So suppose I have 1,000 different items. You've seen 5 of them. I will sample over those 5, but I won't go into the other 995. So this means that you're certain that your system is going to be moderately okay. Like you won't be doing very bad actions. But this also means that because a large part of the action space is not explored, it's much harder data to learn from. Because you basically want your model to know that it doesn't know a lot of stuff about your things. And that is basically why the value-based models are going to fail, because a normal value-based model doesn't know that it basically has a very bad estimate. You can use stuff like the variance of the prediction and stuff like that, but that is not something in the scope of this work. But so to fix that, you can move towards a logging policy that still does that same thing. So it's going to randomize over those 5 actions instead of the entire XP of 1,000 with a very high probability. But with a very small probability, you're going to go uniformly over the rest of the actions. And then you have to tune like this sort of hyperparameter, which means how sort of often are you going to take a uniformly random action. And of course, the more you do that, the worse your CTR of your life system will be. But you might actually be able to learn better in the future with the data that you collect from a random logging policy. And then, of course, for a very large values of epsilon, for 1, of course, this means that you are just going to take an action uniformly at random the entire time. And then it's going to be much simpler to learn from, because every context action pair is sort of equally likely to appear in your training sample. And this is going to be very nice, because now the quality of your reward estimator is going to be uniform as well, which is great. But of course, this is not something you really want to do in a live system. Just show stuff completely uniformly at random. And then if you go to results, you see why that here for the uniform logging policy, the actions, like the most of the policies actually perform pretty well. But when you move to the one that's only randomizing over a much smaller part of the action space, you can see that they're all doing much less good. Like most of the sort of existing approaches here really just attain a fraction of the reward that they would have gotten if their training sample had been better explored.
Awesome. That actually makes a lot of sense. Cool. Okay. So, do you have any questions, Susan?
Oh, I actually do have one more question. So,
Right.
you had a slide. I guess it's like the notation for A being a one-hot encoded vector for the actions. And I'm wondering if maybe it's not denoted in A, rather, but in this series, I guess in this research, is there accounting for the fact that, let's say, an item space could change during, or is it assumed to be held constant in this case? I just want to understand, like,
Right.
make
So
sure.
for us, it's going to be constant. So suppose you would have a new item. I actually haven't thought of this yet, so now I'm just going to think out loud. So I might say very stupid things. But so assume you have a new action. This basically means that you would need to learn, in this case, you would need to learn some new parameters. But that would be an option, right? I mean, it's not super simple or super straightforward, but I mean, I'm assuming you could sort of add an arm basically on the fly. Supposing that you would be sort of training online and you would get a new batch of training data. If there's an action that you haven't seen yet, you can just grow your vector of parameters. You can add sort of an new parameters, have a sort of random initialization, and then do an update with data for that new action. So yes, that is something you could do, not super straightforwardly, but it's not something we did in this work.
I see. Yeah, I just wanted to kind of understand that, because I guess implementation-wise, I can imagine how it might work. But then if you had done it, then I wanted to hear how it would have.
Oh yeah, of course. Yeah.
Exactly.
Yeah. No, I mean, I would say in general, it's not super easy. I would also, yeah, because then certainly when you have this new action, if it's going to appear at a certain time, this means that for the entire time until that time, that action was never taken by the logging policy, right? Because it didn't exist. So it's going to have a logging propensity of 0, which is a problem, because then you can't really do IPS, and then you have all of this stuff. Yeah, which might actually be an issue.
Yeah, totally. Awesome. Omar,
Awesome.
did you have any other thoughts as well?
No,
or?
I think I actually I was going to ask that question, but that's fine. Okay. So I think I don't see any more questions. Okay. For that being said, first of all, thanks a lot for attending Olivier. It's really nice to have you. Looking forward actually for your next research. Your work seems super interesting.
Thanks.
And thanks everyone for listening to this video. So again, please visit ai.science and subscribe to our YouTube channel, ML Paper Explained, to get all these free content right away. We also provide premium content for like workshops in different parts of machine learning. So again, thanks everyone for attending. Thank you, Susan, for helping us out.
Thanks.
Thank you.